Hello and welcome. This is a work through of 93202 Scholarship Calculus 2025 examination. In this video, we'll just do question 1. There's 4 parts to it. So let's get started. The key to this first question is to recognize that 125 is equal to 5 cubed, and to apply the rules x to the power of a to the power of b equals x to the power of a times b. And in fact, we'll see that applied a third time. If you have this tower x to the power of a all to the power of b all to the power of c, you get x to the power of the product abc. We're going to have to solve a cubic as well later, but we'll look at that as we go on. So if we just rewrite this, but rewriting 125 as 5 to the power of 3 all to the power of x cubed minus 5x squared plus 11x minus 3. It's the cube root. A cube root is the same as the fractional power 1/3, and that's equal to 5 to the power of 4 x squared plus 12, and all of that is a fourth root, which is the fractional power 1/4. Now, applying this rule and this rule to both sides, over on the left-hand side, we've got a third here and we've got 3 here. When we multiply those, we're going to get 1. So we're just going to be left with 5 to the power of the cubic, which I managed to write inappropriately. X cubed minus 5x squared plus 11x minus 3, and that's equal to, and this is a quarter times this, so we can multiply each of these coefficients by a quarter to get 5x squared plus 3. Now, since we've got the same base on each side of the equation, that means that the exponents will have to be equal, so we can write this simply. Sorry, I'm having a bit of trouble with my pen. X cubed minus 5x squared plus 11x minus 3 is equal to x squared plus 3. Now, putting this in some sort of standard form, which is put all of the terms on one side, the left-hand side, we've got minus 5x squared here, and we've got x squared on this side. We'll subtract that to get minus 6x squared plus 11x, and we've got minus 3 and plus 3 on the other side. Subtract that, we'll get minus 6 equal to 0. And now we've got a cubic that we need to solve. Perhaps you can use a calculator. The way that I was taught as a student was to start with just a trial and error type approach to find one solution and then do some factorization from that. And for this particular question, it's quite easy. So you just start putting values of x in and see if you can get somewhere. Sometimes you will be able to quite easily, sometimes you won't, and you'll have to use some more sophisticated technique. In general, there is a method for solving cubics, but it's not taught at this level. It's quite interesting, and it's especially interesting in terms of complex numbers. But if we put x equal to 1, which is where I would start, you don't start at 0, because we know 0 straight away is this minus 6, so 0 can't be a factor when you've got a constant coefficient at the end here. But 1 cubed is 1, minus 6 times 1 squared is 6, plus 11 times 1 is 11, and minus 6. You can see straight away that that is 0, and that tells you very, very quickly that x minus 1 is a factor. So we found one solution straight away. I reckon the easiest way from here is sometimes called synthetic division. You can do a long division if you want. And what that works like is we've got x minus 1 as a factor, and we want to build up another factor that's going to be a quadratic factor, and we need that to be equal to x cubed minus 6x squared plus 11x minus 6. So we need x times something to give us x cubed, and that clearly has to be x squared, so we need an x squared term there. But as soon as we put that in, we've now got minus x squared. So we want minus 6x squared, so we need another minus 5x times the x to give us minus 5x squared. That in turn gives us plus 5x, but we want plus 11x, so we need another plus 6x to get that. And just checking, minus 1 times 6 is minus 6. That gives us the constant term. So we've done the division in a quite straightforward manner. X minus 1 is already factored. This is a straightforward quadratic to factor. We need two numbers that multiply to 6 and add to negative 5. Quite clearly those two numbers are negative 2 and negative 3. And therefore x equals 1, x equals 2, and x equals 3 are our solutions of the equation that we needed to solve. Part B. This is going to be a quadratic equation when we multiply through by x, but basically whenever you see something in the denominator, a good strategy is to multiply the whole equation by that denominator, and that will get rid of the fraction for you. Actually, in this case, I'm going to suggest multiplying by just the z first, and I'll deal with the I later. We'll see why that turns out to be straightforward, and I like it. But I mean, you could try multiplying by iz. You'll be fine. You'll just get some complex coefficients of all the terms. But if we multiply through by z, z times z is going to become z squared. 2 times z is 2z, and this bit here is minus 2 plus I over I, because we've cancelled the z out. And now, just this fractional term, I'm going to multiply by minus I over minus I. And the advantage of that is I times minus I is equal to 1. I times I is I squared is negative 1. Negative of negative 1 is 1. So we get z squared equals 2z. And now multiplying this out, minus is plus 2i. I'm going to write that on the far right. And minus times I, minus I times I times I is negative 1. So we get negative and negative 1, positive 1 there, but there's a minus sign in front, so we get minus 1 here. So minus I times minus I. Minus times minus is positive. I times I is I squared. It's negative 1, so that gives us the negative there. Now, we might notice that if we put these two terms onto the other side, we've got a perfect square here. So I'm going to do that, and I'm going to leave 2i over on the other side. And this is z minus 1 all squared equal to 2i. And now we can take the square root. So z minus 1 is going to be equal to plus or minus the square root of 2 times the square root of I, if you like. This is like doing a completing the square, putting those terms on. We've got a complete square on this side, and we put everything else on the other side. You could put everything over here, then complete the square. But the process then would be shifting back. You could solve this equation with the quadratic formula. You put this on the other side, and you'd have to use 1 minus 2i as the c value. I like this approach of which is effectively a completing the square approach. We need to just investigate about the square root of I, and argon diagram, I is up here. Square root of I is going to lie on this diagonal pi over 4 as the radians, as the radians of the argument, the radian measurement of the argument. So it's the square root. We've got the square root I is 1 cis pi over 2. So the square root of I is going to be 1 cis pi over 4. We do have to add on an arbitrary amount of pi, 2 pi over 2. So we get cis pi over 4 or cis 5 pi over 4. Yeah. Cos pi over 4 plus I sine pi over 4. Cos pi over 4 is 1 over root 2 plus I sine pi over 4 is also 1 over root 2. So this is the square root of I. So over here this is plus or minus square root of 2 and then times 1 over root 2 plus 1 over root 2 times I. The root 2's cancel, so we get plus or minus 1 plus I. Not done, am I? We've got a z minus 1 on this side, so z is equal to 1 plus or minus 1 plus I. And that's 1 plus 1 is 2 plus I, and or 1 minus 1 is 0, 1 minus I is minus I. So these are the two solutions of this equation. Part C. How many different complex solutions does the equation z to the power of 2025 equal to the conjugate of z, complex conjugate of z, have? Well, I think a good start is to write not R, write Z. Z equal to R cis theta. Then Z conjugate is R cis minus theta. That's how they're related. So if we've got Z here somewhere, angle of theta, the conjugate of Z's down here. This is the same angle. So we're going in the opposite direction, so it's minus theta. Hence we get this value in here. And then write out the equation. So we got R cis theta to the power of 2025 is equal to R cis negative theta. And we're trying to solve that. We don't actually have to solve it, we just have to find out how many solutions there are. De Moivre's theorem says we raise the modulus to the power and we multiply the argument by the argument, and that's going to be equal to R cis minus theta. Two complex numbers are the same only if their moduli are the same and their arguments are the same. So we're going to get two equations here, one for the modulus, which is going to say R to the power of 2025 equals R. That's the same as r to the power of 2024 times, no, wrong way around. That's the same as saying r to the power of times r to the power of 2024 minus 1 equals 0. I've just shifted the r to the other side, then taken a factor of r outside, and done that badly. And this equation has one solution, r equals 0, and it has another solution, r to the power of 2024 has to equal 1. Our r here is always a real number, and it's always positive. So the only way you can solve this second part is if r equals 1. So that they're the two moduli that we're working with. When r is 0, that's just the complex number at the origin here. The argument doesn't matter. It's one solution, r equals 0, whatever. Yeah, so this is one complete solution. This one here just tells us what the modulus has to be, and we still have to figure out what the argument is. So let's move on to the argument. Doesn't matter for r equals 0, but it matters when r is 1, and the two arguments up here have to be the same. So 2025 theta has to equal minus theta, but of course there's the standard complication that to get theta you can go around a full circle and then add on theta. So we can go around 2 pi, and we can do that multiple times. So if we go around k times, all of equations of this form for various values of k will give us solutions. We can tidy this up by adding theta to both sides, so we get 2026 theta is 2k pi, and that means that theta equals 2k pi divided by 2026, and we can see that we want to put in various values of k, and we can see that all the way up to 2026 we'll get different solutions. When we get to 2026 divided by 2026 is going to cancel, so we'll be left with 2 pi. That's the full circle. That's the same as 0. So this gives us a unique solution for any k in the range 1, 0, 1, 2, all the way up to 2025. We start repeating at 2026. You can actually use different values in here. You could use some negatives from negative 1013 up to 1012 or something, but they just need to be 2026 contiguous values. So here we've got 2026 solutions. Here we've got one solution. Solutions. So overall, therefore, there are 2026 plus 1, which is 2027 solutions. In fact, we've done better than that because we've actually found the solutions. So the solutions are z equals 0, z equals 1 times cis 0, z equals 1 times cis 2 pi over 2026. Z equals cis 4 pi over 2026, all the way up to z equals cis 2025 pi over 2026. We weren't actually asked to find the solutions, but as I say, we've constructed them, so it's useful, at least for understanding purposes, to write them down, even if we didn't need to calculate them in the question. Part D. Here we've got 4 complex numbers. We've got Z, which we're told we can write in this form, and we've got Z conjugate 1 over Z and IZ, and we've got to do some working with those. So I reckon it's a good thing to write down to start with what they are. So Z is R cis theta. Z conjugate, we saw this in the last question. We get the conjugate by negating the angle. 1 over Z. This is a simple application of de Moivre's theorem. 1 over Z is the same as Z to the power minus 1. So that's R to the power minus 1. And cis minus 1 times the angle, so it's minus theta. So 1 over R cis minus theta. And this is interesting because these 2 complex numbers have got the same argument, so they will lie on the same radial line out from the origin, which we will utilize in just a moment. And I times Z, it's possibly easier to explore this if we write this as cos theta. Well, even just write it as it's going to have a form x plus yi. So it's I times x plus yi, which is ix, xi. I times I is minus 1, so minus y plus this. And then if we draw a picture, we can get a better handle on this. We've got our theta over here, so our x and our y. And this number here, it's minus y, so it goes back that same distance, and then up x. So we get this triangle and this complex number up here. So this is z, this is iz up here. And it's pretty easy to see from basic geometry that this angle in similar triangles, this angle has got to be the same as this angle here. So because we've got the same real and imaginary parts but swapped, the modulus is going to be the same, so we're going to still get a modulus of R, and our angle is going to be a right angle plus theta, pi over 2 plus theta. So I think that's going to be a useful form for us to use. Now, the question says BC is 1.5. Let's I'm going to rub this out later, but let's just put some points on here somewhere. Say we've got A up here, we've got B down here. We'll get them more accurately later. It's the conjugate, so it's straight down. What we found, 1 over Z is on the same line, and it's, well, 1 over Z is going to be, for a modulus R greater than 1, 1 over R is going to be less than 1. So we've got a C point down here somewhere. And we've got D, so we've got this angle. We need to have a similar angle out here somewhere. And it's going to come up somewhere here. And we'll get D. So we've got some 4 points. And as I said, I'm going to erase that later and try and draw them more accurately when we know. The first thing, the BC, this is 1.5, and this is just the modulus of B minus the modulus of C. So the modulus of b is simply r, minus the modulus of c was 1 over r, and that has to equal 1.5. I don't like decimals, it's a form of fraction. I don't like fractions, so I'm going to multiply by 2 to get rid of this decimal and multiply by r to get rid of this throughout. So 2r squared minus 2 equals 3r. 2r squared minus 3r minus 2 equals 0. Quadratic. Use your favorite methods. It's got to be 2r and r if they're going to factorize with ordinary numbers. We've always got the fallback position of using a quadratic formula. It looks like minus 2 and plus 1 work. So plus r minus 4r gives us minus 3r. 1 times minus 2 is this. Yes, indeed, this works. So r is negative a half, or r is 2. And negative a half is no good to us because moduli are always bigger than or equal to 0. And in fact, in this question, we're told the modulus is bigger than 1. So we have to have this value here. The other thing we're told in our question is that this angle here is pi over 3, 60 degrees. I don't actually like the fact that they've used 60 degrees here and they've used radian measure up here. I don't think there's any need for them to put both sorts of measures in the same question. They're not really testing that understanding. I'd prefer them to say pi over 3 down here, but anyway, we're working with what we've got. We've got 60 degrees, and that's pi over 3. Now, from the similar triangles, so this is a triangle and this is a triangle that have to be similar. We have to have pi over 3 up here, and so we have to have pi over 6 down here, which is going to be equal to our theta. So that means I think now we're in a position to write down what all these complex numbers are. I've written r again. I want to write z. Z is equal to r, which we've found to be 2, cis pi over 6. Pi over 6, pi over 3, right angle 1, 2, root 3. Cos pi over 6 is root 3 over 2, so this is 2 times root 3 over 2, plus I times sine pi over 6 is a half. The 2's will cancel, so we'll get root 3 plus I. Z conjugate, we could go through the same process, but we know that the conjugate is just changing the imaginary part to its negative. 1 over Z. We've got R is 2 here and a half here for the modulus, and they've got the same argument, so the modulus here is a quarter of that modulus. So, to get a quarter of the modulus, we just take a quarter of each term. So root 3 over 4 minus I over 4, or minus a quarter over 4, and IZ, just multiply this through by I, we're going to get root 3I. I times I is negative 1. Negative, it's this one here, we multiply. Root 3I, I times I is negative 1, so it's negative 1 plus root 3I. So we've got our 4 points, so we now know exactly where these points are. I'm going to try and draw a better diagram of those points. Not going to be perfect, but it's going to be okay. So root 3 is 1.7. So if I make 4 of these 1, so this is 1.75. I'm just going to be just inside that. 4 of these is 1. So I think I get, this is Z. I'm going to label it by the actual number. We got a point down here, root 3 minus I. We've got a quarter of that, so that's going to be where it intersects on this line here. So we get root 3 over 4 minus I over 4 is this point here. I guess I should label the point names as well, but maybe it will help if I give those different colors so everything stands out. And then so minus 1 plus root 3i, so we're over here, minus 1 plus root 3i is up here somewhere. It's minus 1 plus root 3i, and that's point D. Might help to try and use the ruler. I've had trouble using the ruler, the wrong button. I've had trouble trying to use the ruler before, but let's try and find what we are. Use a grotty yellow colour. I'm going to shade it in so we'll be able to see. Comes down here. Car's just pulled up the drive, so I might have to stop and finish this video later. Such is life. Try and get this area done before I stop. Yeah, done. So this is the area that we want to find, and I'll finish this video a little later. Okay, back continuing this problem. We've found the points A, B, C, and D, and we've got the complex numbers that are represented on the picture, and we need to find this yellow area. And I think that the best way to do that is to draw what looks like a rectangle, but it's actually a square all of the way around. This region, and then we can calculate the area here that we want. And what we have here is some triangles, which we'll call T1 and T2. So we have another triangle goes across here, and we've got a trapezium down the bottom, which we'll call T3. And we can work out the area of the rectangle. As I say, it looks like a rectangle, but it's really a square, and that's because basically the dimensions here are not the same. But I've used roughly those dimensions to represent the numbers. So I've got like root 2 out here, and which is 1.7 something or other, and I've got minus 1 down here and minus 1 across here. So it's minus 1 down. It looks further than minus 1 across, but we can calculate. So the difference in the x value, we've got root 3 here and minus 1. So this top side is root 3 plus 1, and the vertical side of that triangle goes up to root 3i, and it goes up to I here. So we're going to have in here, we're going to have root 3 minus 1. This triangle here, we've got root 3 up here, and then this is minus I over 4. So this bit here will be root 3 plus 1 over 4. That's from here down to here. And here, or here across, we're going to have, so it's back to minus 1, and it goes over to root 3 over 4. So we have in here 1 plus root 3 over 4. It's the total distance across. We're running out of space. Let's try a different colour because that will help. Along the bottom, well, we've already got that there. We don't need it all the way down, but we do to calculate the area of the square. So this goes up to root 3, and this goes down to minus 1. So the total distance is root 3 plus 1, all the way from the top to the bottom. So it's the same as the distance across. And so indeed we do have a square. We've got this side, we've got root 3 plus 1 here. We need to have this side here. So this is down a quarter, and this is down 1. So this side here is going to be 3/4. And now we can work out the areas. So the area of the square is root 3 plus 1 multiplied by root 3 plus 1, and that will give us root 3, and root 3 is 3 plus 2 root 3 and plus 1 plus 1 plus 2 root 3. So that's 4 plus 2 root 3. Yeah. T1, the triangle at the top, it's root 3 plus 1 across. It's a triangle, so we have a half. And let's just remind us, it goes down, root 3 minus 1. This is 3 minus 1, which is 2, divided by 2, so this is going to come out as 1. Triangle 2, again, it's a triangle, so we've got half. And what are the side lengths? We've got root 3 plus a quarter, and we've got 1 plus root 3 over 4 going this way. Root 3 plus a quarter, 1 plus root 3 over 4 this way. Now what's that equal to? Well, we've got a half. We take a quarter out of here, take a quarter out of here. That's 4, 4, 16. That's 1 over 32. And we'll have 4 root 3 plus, 4 root 3 plus 1 multiplied by 4 plus root 3, multiplied in each bracket by 4. So it's 1 over 32. The root 3 terms, we've got 16 here, and we've got 1 here, so we've got 17 root 3. And the ordinary numbers, we've got 4 times root 3 is 12, plus 1, we've got 16, plus root 3 over 2. And the trapezium, which we've also called T, triangle and trapezium, start the same letter. The formula is similar, isn't it? So we've got the top plus the bottom times the height, and then half of that. So we've got half. The height was 3/4. The top is 1 plus root 3 over 4, and the bottom is root 3 plus 1. 1 plus root 3 over 4 plus root 3 plus 1. Now we can take the quarter out again, so we get 3 over 32, and here we're going to have 4 plus 4 is 8, plus root 3 plus 4 root 3 plus 5 root 3. Which is 24 1 over 32, 24 plus 15 root 3. So the total area is going to be the area of our square, 4 plus 2 root 3, and minus each of these things here. So T1 was 1, T2 was 3 over 32 times 8 plus, and I've skipped, T2 was 1. One over 32 times 16 plus 17 root 3, and T3 was 1 over 32 times 24 plus 15 root 3. So this 4 minus 1 is 3. 16 over 32 is minus a half. 24 over 32 is 3 quarters. And here we've got 2 root 3, and we've got minus 17 root 3 over 32, and we've got minus 15 root 3 over 32. So that's minus 32 root 3 over 32, so that's minus root 3. So we're going to have just plus 1 root of root 3, and the ordinary numbers are 3 minus a half is 2.5, minus 3 quarters is 1 3/4, 7 over 4 plus root 3. And we're done there. Hopefully I'll be able to merge those two videos, and we have question 1 complete. So thank you very much. Any questions in the comments? Otherwise we'll move on to question 2 in the near future. Hopefully I managed to merge 2 videos, so if I can do that I can merge 3 videos. I'm just revisiting part C, just a small error here at the end. The formula is 2k pi, so when k is 2025 you get z equals cis 2 times 2025 pi over 2026. So I've left out a 2 in here. So now that's corrected that, so hopefully we're all good, and I will see you in the next video.